Hello and welcome. In this video, we are going to take another look at our numeric vectors in Matlab. We can think of these as one-dimensional arrays. We'll be handling multiple dimensional arrays in later videos. Specifically in this video, what we're going to do is we're going to look at some of the basic operators as they are applied to vectors. Now, this video assumes that you've been following along with some of the videos that are earlier in this series and particularly know how to create a vector. And what we're going to do is we're just going to apply some common operators to a vector. Now, I provided you with a couple of links, including the list of Matlab operators. We're only going to be looking at a few of them in this particular video, and we're going to introduce a couple of new ones to show you then how you can interact with vectors a little differently than with your scalar values. And so to begin with, what I'm going to do is I'm going to simply create a vector. You can call it my count up vector that starts at 0, increments by 1, and then stops at 10. And so the result here is going to be a 1 by 11 vector of doubles that we're going to use to demonstrate some of our operations. Again, I'm going to leave the semicolon off because I do, in fact, want some noise in the command window. Now, what I'd like to do is I'd like to essentially go through by demonstration each of the basic operators so we could figure out then how element-wise operations work in Matlab on vectors. And then ultimately, you'll see that the behavior is very similar with arrays. And so what we're going to do is we're going to add to our A vector simply a value of 1. And you probably won't be too terribly surprised by the results, but you can see down here in the command window that effectively what I'm doing is I am adding 1 to each of the individual values in the vector A. And so a good way of describing this is just simply going to be element-wise addition of 1 to each of the elements in A. So again, just to emphasize, you'll notice that the first value of A is 0. I'm simply adding 1 to it. And now in B, I have a value of 1. Second element in A is 1. 1 plus 1 is 2. And then you can go all the way out to the last element. You can see then the last value is 10. And I'm simply adding 1 to it to get 11. Well, guess what? You can do the same thing now with the subtraction operator. So in other words, in this case, if we were to, again, subtract each value from, or 1 from each value in A rather, and let's go ahead and pull up A next to C, and you can see that basically all we're doing is, again, just element-wise subtraction of 1. In other words, every element in A is treated individually, and simply subtract 1 from each of those elements. So again, I'm going to put a little note here. This is going to be element-wise subtraction of 1. And then you can probably guess that we can do the same thing now with our multiplication, except, in other words, to make it a little more interesting here, we're going to multiply by 2. And again, I'm going to run this, and then I'll go ahead and pull up both A and D in the window here so that we can see. And again, not too big of a surprise. We're simply taking each of the values of A, and we are multiplying it by 2. And so 0 times 2 is going to be 0. 1 times 2 is 2, all the way out to 10 times 2. So again, this is an element-wise operation. So this is going to be element-wise multiplication by 2, and then the next logical example is just going to be then our division of A by 2. And again, if we run this real quick, put these two side by side. There's our A, there's our E. And you can see that it's, again, pretty straightforward. It's just going to be element-wise division of each of the values. So again, put a little note here, element-wise division by 2. And essentially just remember that when I say element-wise, I'm treating each element individually, and we're applying the operation individually. Now, there are some exceptions, if you would, to this very simplified comparison between the scalars and vectors, scalars being a singular value. In other words, just a quick refresher here. If we were to simply multiply 2 times 2 together, no big deal, and we get 4. And if we were to raise 2, let's say, to the 3rd power, we would simply use a little caret or the hat symbol, and we would get 8. Well, it turns out there are some cases in which this doesn't work out quite this easily. And specifically, when we are looking at multiplying two vectors together, or we are doing some operation that involves a vector, such as raising it to a power. And so to understand what I'm talking about here is, let's use that last example where we took 2 and we raised it to the third power. And what we're going to do is we're going to do it 2 different ways. We're going to start off first by taking the original A vector, and we are going to essentially square each of the values in A. And if you run this right here, you'll see here that we get incorrect dimensions for raising matrix to a power. And so what you're going to see here is that we need to use the dot caret or the dot hat operator. And so in this case, what this does is this will then raise each of the individual elements in A to the power of 2. And so we'll put A back up here. We'll compare it to F, and you can see that 0 squared is still 0, 1 squared is 1, 2 squared is 4, and so on all the way out to 10 squared, which is 100. And so you can see here that while this is still the element-wise exponentiation, the difference is that we have to change our operator then from the caret to the dot caret to be able to pull off this element-wise exponentiation. And the same is true then if we were to do something like this. We're going to actually take our 2 and we're going to use the same vector here. We're now going to say 2 raised to the A power, and you can see that we're going to get an error here that says incorrect dimensions for raising a matrix to a power. And again, if we simply replace this, then what we will get is we will get 2 raised to each of the powers in the A vector. And again, let's go ahead and pull up the original A vector followed by the G vector. And we might have to spread this out just a little bit to get both of those vectors in the same screen here. See if we can accomplish this. There we go. That's close enough. Maybe a little bit more here, but you can see here that basically what we've got is now 2 to the 0 is 1, 2 to the 1st is 2, all the way out to 2 to the 10th, which is going to be 1024. Again, though, same thing, that when we are dealing with vectors, we need to use the dot caret in certain scenarios, okay? And again, we're going to just simply leave it at that for this particular example. I've provided you with the link that gives you a description of where, in some cases, that you need to use the dot equivalent of each of the operations. There is one more particular example that I do want to show you before we leave this topic, in that I'm going to go ahead and try to multiply A against itself. In other words, I'm going to multiply 2 copies of A, or I'm going to try to add 2 copies of A. So let's go through just a couple more examples here. So what if I added A plus A? Well, sure enough, that's not a big deal as long as A is the same size as whatever you're adding it to, or a scalar. In other words, basically A in this case is a 1 by 11. We're multiplying, or adding rather, 2 1 by 11 vectors together. No big deal. However, though, if I come along and let's say I create another vector, in this case, I'm going to again simply use the colon notation, but I'm going to intentionally make it a little shorter here. I'm going to start off at 1 and I'm going to end at 10. Notice here that this is going to be a 1 by 10 vector. And then if I try to add my A to my J vector, because they are not the same size, you're going to get another error here. So arrays have incompatible sizes for this operation. And so the trick here is, in order to be able to add 2 vectors or 2 arrays together, they are or must be the same size. And in this particular example, they are not the same size. And so as a result, you get an error. And what do I again mean by that? Well, our A is a 1 by 10, and, or excuse me, our A is a 1 by 11, and our J is a 1 by 10. And so effectively what you can think of is that you don't have enough values in J to add to the original A vector. The same thing is true when you do subtraction, multiplication, or division, with one minor catch. And so that again goes back to the example that we did with our exponentiation. So let's try to do something really strange. Let's try to multiply our A against itself. And so in this case, we're at K, we're going to assign the value here to L. And so essentially what we're going to do is we're fundamentally squaring, if you would, our original A vector. And again, we're going to get an error. It says error using just that star, that multiplication, because we don't have scalar values. In this case, basically what we're doing is we're multiplying a vector times a vector, or an array times an array. And the easiest way to get around this is just simply to use the dot star notation. And again, what happens here is you go back to that element-wise multiplication. And so in this case, it's element-wise multiplication of two vectors. And again, this works the same with arrays. We'll take a look at that then in a later video. The overall point is with this is that operations on vectors are relatively similar to operations on scalars, with some slight exceptions. In other words, you need to be aware of whether you're dealing with a scalar when you are doing things like exponentiation as well as multiplication. Now, I will say that in my personal experience, that typically there has not been any performance detriment when just simply using the dot star or the dot caret notation when you are dealing with both scalars and vectors, because technically MATLAB treats a scalar as a 1 by 1 array. However, though, it may be a good idea to keep in mind with certain operations that there may be a performance hit. The other thing to note here is that if you take a look at the MATLAB operators and special characters, particularly when you start looking at the different types of division, that there is going to be some behavior changes between whether you are dealing with a scalar or a vector or an array. But again, that's way outside of the scope of this particular video. Hopefully you found this video useful. As always, if you have any questions, comments, or concerns, thank you for watching.